The key feature of our 10-qubit demonstrator, I think, is the enormously good quantum coherence of the chip that promises a very, very high performance in terms of a low error rate. That is embedded in a very consistent software stack that allows to use this very efficiently, but it's also surrounded by a whole suite of enabling technologies that make it clear that we have a good ecosystem moving forward. So the main hurdle we had was to really get the central processor. We started with an excellent team that still, when the project started, was building its lab and building a laboratory in a time of global supply chain interruptions due to global crisis and war, meant that we had to battle with a lot of delays. And in the fabrication of these chips, there are hundreds of little steps that need to go well. And fortunately, right before the deadline, we had a batch of chips where everything worked, where none of the many project steps was limiting the performance, and that was a great relief. So currently, as we are speaking, right before Christmas in 2024, the device is behind the curtains of Jülich in the sense that the software infrastructure is ready, but the calibration and the tune-up of the system is ongoing. And once this is completed, it will get live, first for users of the project, but outside the Forschungszentrum, so we can collect some experiences and then ultimately for full access. So for us, there are clearly two lines. One is to develop and test first disruptive quantum applications. In this system, which is home-built, so it's a lot more flexible than the commercial system that the Forschungszentrum also has, we expect that in some applications, specifically in scientific applications, so where the user is another part of science, we will be able to do some first demonstrations. It is also important as a test bed for quantum computing developers, so for researchers who are looking at improving quantum computers and understand quantum information, again, because of its high flexibility. As we are scaling up, we hope that in some applications that require a low error rate, we will be a viable alternative also to commercial offerings. Yes, absolutely. We have synergies with other projects. One of the challenges that we have in Jülich is to make sure that the workflow between the classical supercomputer and the quantum computer is really efficient and which is really seamless. And we are sharing a joint design philosophy. We are also having a shared user interface. The closer we get to the hardware, the more these systems get to be separated. But tools in the software stack, like the compiler that translates the human-readable programming language to a machine-compatible programming language, are fairly similar. So the meeting in Ulm was very crucial. It was a very, very focused work meeting because on the one hand, we were looking for all of our many partner contributions. Where are they standing relative to their own milestone? Do they need support? It's basic research, or not basic research, it's research. So sometimes we meet the milestone in a way that is not how we thought we would meet it. We need it another way. And this we could all clarify, and we could already identify that many partners were doing well. At the same time, we were at the moment when the last fabrication step failed for a rather simple reason. So we had to focus on all kinds of strategies, how we get to a convincing processor, and what we do if we don't have one. Fortunately, that problem solved itself about 3 weeks later, but that was the key. So we saw that we could kind of focus on the final stretch with a few open questions, specifically the processor that actually had a problem when the wafer was cut into chips. Yes, the meeting in Vals was very different from the previous meeting in that now we have a system. It's still a few steps and characterizations still need to be done, but all of the partners were now focusing, this is the system, this is what we are going to improve. Also, in the first phase, we had built a few capabilities, for example, in material science, for example, in the readout system, and parts on the software stack, where we had made the plan to make a strategic decision in the middle what we are going to focus on. What of our new material technologies would actually be a viable candidate to go to the critical path in the second phase. And we had quite a number of discussions on these crucial decisions, because now we simply know a lot more than at project start, because we have done multiple years of research.